So let's look at antiderivatives on our way to a fundamental theorem of calculus type result for the complex setting, section 4.44, antiderivatives. Let's recall with a quick recollection of what the fundamental theorem of calculus says. Part 2 tells us how to evaluate definite integrals, and we're all about definite integrals. Fundamental theorem of calculus, part 2 from calculus 1 in the real setting says if integrand f is continuous at every point of the interval a to b, and if capital F is any antiderivative of lowercase f, the integrand, on that interval, then the definite integral from a to b of lowercase f of x dx is capital F of b minus capital F of a. So fundamental theorem of calculus tells you evaluate definite integrals the way you're so familiar with evaluating definite integrals, that is, using antiderivatives. You spend a big piece of your time in calculus 2 and a bit of time in calculus 1 trying to figure out how to find antiderivatives, because anti-differentiation is hard, and in some sense some functions can't be anti-differentiated. By the way, the fundamental theorem of calculus part 1 basically says there's an inverse relationship of some sort between anti-differentiation and differentiation, or more appropriately, definite integration and anti-differentiation, differentiation, which leads us to say we can use antiderivatives to evaluate definite integrals. Part 1 you probably use not very often. It comes up in differentiating, I think, the natural log function when it's defined cleanly, and you don't deal with the early transcendentals in calculus 1. But we want something like this for ourselves. We want something like this for the complex setting. So the plan is, what can we do in the complex setting that relates antiderivatives and values of integrals? Theorem 4.44.a is the big result of this section. The proof's in the next section. We'll probably gloss over that. It says, suppose that a function, f of z, is continuous on a domain D. Okay, so far so good. Talking about continuity up here, all right, the required continuity of the integrand in the fundamental theorem of calculus. The following are equivalent. So they're not claiming that continuity gives these, but any one of these gives either or both of the other two. The fact that lowercase f of z has an antiderivative, capital F of z throughout D, is equivalent to the integrals of lowercase f of z along contours lying entirely in domain D and extending from any fixed point z1 to any fixed point z2 all have the same value. That is, we want to integrate from z1 to z2 f of z dz. All we do is take the antiderivative, plug in the endpoints, just like the fundamental theorem of calculus. So that right there says we've got a fundamental theorem of calculus if lowercase f has an antiderivative valid throughout domain D. Or both of those are equivalent to the integrals of f of z around closed contours lying entirely in D all have the value 0. So now if it comes to using this, it's part A. We want to take part A and say, okay, I can find an antiderivative. If I can find an antiderivative, then I can use it to evaluate definite integrals calculus 1 style. The third observation is no big surprise given the second part. Part C is no surprise from part B. Hey, in part B, if we were going along a closed contour, we'd be going from Z1 to Z1, and we'd have capital F of Z1 minus capital F of Z1. So if integrals around contours, closed contours, are always 0, then that's certainly consistent with this second part. Now, actually establishing that integrals around every closed contour lying inside this domain provides values of 0, that's probably not something we'll do directly. But it's an implication of the other things in terms of applications. You want to think, if we can find antiderivatives, then nice things happen. Fundamental theorem of calculus style things happen if you can find antiderivatives. Okay, and there's some problems with antiderivatives, not just the calculus 2 kind of problems where they're hard to find. We got, especially with that 1 over z function, we got some weird stuff going on with that 1 over z function. We got some weird stuff going on with branches of the logarithm as well. If we want to integrate around closed contours, then the branches of the logarithm are going to be dicey to deal with. And we've even seen some examples already about that. Proof of this is in the next section. Let's talk about using it in this section. Okay. If we had a polynomial function, excellent. Polynomials, they're entire functions. They're differentiable everywhere in the complex plane. They have antiderivatives, and the antiderivatives are easy to find, and they're valid in the entire complex plane, and they're continuous. So if you want to integrate from any contour joining z1 and z2, the integral from z1 to z2, p of z dz, all we need is an antiderivative capital P, plug in the endpoints, z1, z2, take a difference, there you go. Piece of cake to integrate polynomials. Of course, the pragmatic takeaway from this is, well, we're probably not going to integrate polynomials. I mean, that is enough said about polynomials right there. Straightforward, antiderivatives exist, they're continuous. Theorem 4.44.a says fundamental theorem of calculus it with polynomials. How about 1 over z squared? That's a little more interesting than a polynomial because it ain't defined at z equals 0. So consider integrand of 1 over z squared and a contour z equals 2e to the I theta, theta ranging from negative pi to pi. So that's a circle of radius 2 centered at 0. We're going all the way around 0, which will become an interesting thing to consider for some other functions. For this one, the story is going to fall a little flat. But in the next example, we're going to look at 1 over z. 1 over z is going to take us into logarithm land. And that's not a place where we've got continuity everywhere. And theorem 4.44.a, we needed a continuous antiderivative throughout domain D, wasn't it? Has an antiderivative. Let's see, the integrand is continuous and has an antiderivative throughout D. We'll have problems with antiderivatives throughout the domain. We got problems with continuity too. This one, not so much. F of z equals 1 over z squared, integrate around a circle of radius 2. As long as we stay away from 0, we're okay. We can go around 0, which is what this contour does. Can you find an antiderivative? Certainly. Capital F of z, negative 1 over z, differentiate it, you get positive 1 over z squared. It's an antiderivative. It's good everywhere except at 0. So we do have to stay away from 0. There's no division by 0 in any of this stuff. Okay, so we've got continuity. Because the domain we would consider would be this, everything except for 0. Take that to be D, domain D. D was an open connected set, which this certainly is. It's not simply connected, something we'll address in a couple of sections, but it's an open connected set, so there's domain D. The function's continuous on this domain. The only place it ain't continuous is at 0. The antiderivative is valid everywhere, well, except at 0. So you want to evaluate the integral? We can use the antiderivative. But wait, that's a closed contour. If you like, the way it's parameterized, I'd be prone to say it starts at -2 and goes in the counterclockwise direction around a circle of radius 2, ends at -2. So closed contour, that integral is going to be 0. Or if you like, we can take the antiderivative, -1 over z, and evaluate it at the 2 endpoints. But both endpoints are -2, the way it's parameterized, and that produces 0 as well. So part B will give us that the integral is 0. Part C of that theorem will give us the integral is 0 as well. We may expect many integrals along closed contours to be 0. Yeah, if we deal with nice functions, these integrals around closed contours are going to be 0. So that means we need to talk about not so nice functions. Here comes logarithms and potentially square roots because they're based on logarithms and cube roots and so forth. Example 4.44.3 has you considering 1 over z. All right. Well, 1 over z is going to lead to some dynamic behavior, some not so nice behavior. Okay. We don't have an antiderivative that's valid on any domain, say, that contains a contour C that we were just looking at, a circle of radius 2 centered at the origin, say starting at -2, positively oriented, counterclockwise, and ending at -2. We can't find an antiderivative of this function that's valid on that contour. That's because we need to use a branch of the logarithm, and the branch of the logarithm comes with a branch cut. You'll remove 0, and you got to cut it. And when you cut it, you peel up that line from 0 to infinity. That's going to cut the contour as well. So we can't find an antiderivative that's valid on the contour. We go back up here, has an antiderivative valid throughout domain D. We throw 0 out and we're good, but we've got to cut the thing as well. And that can't be done if we're going to have a contour lying entirely inside D and use say the part 2. So let's do what we can with this one. And the 1 over z function, I can't use that theorem on this one. If I could, this integral will be 0. Okay, by part C or part B. So we're going to show the integral ain't 0. Turns out the integral is 2 pi I, which ought to ring a bell in connection with log functions. Log functions, exponential functions had periods 2 pi I. And that certainly has an impact on log functions. There's something with the 2 pi I related to the log functions as well. It's the argument, how the argument varies. All right, so here's our contour. We're going to break it into 2 pieces and deal with this integral piecewise. By so doing, we can find antiderivatives on pieces of the contour, and we'll just paste them together. We'll just add them together. Okay, so let C1 be, we're taking that contour and restricting the angle to be between negative pi halves and pi halves. So instead of, let's take a look at the figures down here, instead of going from -2 all the way around back to -2 in the counterclockwise orientation, we're going to take the right-hand half and the left-hand half. We'll figure out this integral, we'll figure out that integral, and we'll add them together. And that's a perfectly legitimate way to compute the integral all the way around 0. Got to do this piecewise stuff because I can find branches of the logarithm. So this picture foreshadows how we're going to do this. I can find branches of the logarithm that don't cut, say, the right-hand half of that circle. This is a principal branch of the logarithm. It looks like they're using. Remember, we cut along the negative real axis for the principal branch. We could cut anywhere you want to, remove 0 in a line. We could cut along the positive real axis. That ain't the principal branch of the logarithm, but it's a branch of the logarithm. All right, that won't cut the left-hand half of that contour. So we're going to deal with different antiderivatives, but antiderivatives that allow us to use Theorem 4.44.A on the pieces of the contour. Okay, so C1 is the right-hand half of the contour, and we'll use the principal branch of the logarithm. Recall, log z is capital L log z, principal branch of the logarithm. Is a natural log of r plus I capital theta. R is the modulus, has to be greater than 0, and theta is between negative pi and pi. Theta is between negative pi and pi. Right. We remove negative pi. We remove complex numbers with arguments of negative pi and anything coterminal with it. So usual principal branch of the logarithm stuff, back to the computations, okay? Principal branch of the logarithm, differentiate it, you get 1 over z, where it's defined. It's defined on a place that includes contour C sub 1. Yeah, there you go. So we'll take a different domain. We'll take domain D to be C minus the branch cut for the principal branch of the logarithm. That's what they're illustrating in figure 50. Domain D is the entire complex plane with 0 removed and the negative real axis removed. And we're looking at a new problem. With that domain, we've got an antiderivative of 1 over z. It's the principal branch of the logarithm. It's defined throughout domain D, and C sub 1 lies inside that domain. Okay, so we'll take, this is the domain. On that domain, everything's fine. You want to integrate over C sub 1, 1 over z dz. You got yourself, typo there, you got yourself an antiderivative, principal branch of the logarithm. So when we integrate, we get the principal branch of the logarithm evaluated from the endpoints. We've set it up where the endpoints are negative 2i to 2i. So those are the z values. So we'll take the antiderivative. Here we are up here. Take the antiderivative, evaluate it from negative 2i to 2i. Plug the endpoints in. Use the principal branch of the logarithm, which really just tells you how to choose the arguments. And when the dust settles, we get pi I. Remember, that's only half of it. Okay, secondly, we'll do the same thing. We'll get pi I out of the second part too, it turns out. Take C sub 2 to be the left-hand half of the circle. In this case, we'll take the domain D to be complex plane minus the non-negative real axis. All right, so we've removed 0 and the positive real axis here. For the domain D, contour lies entirely inside that, and we've got a branch of the logarithm that's legitimate, continuous and everything, on C sub 2. It's not the principal branch. It'd be a branch that throws out, say, 0 and anything coterminal with it. So the branch of the logarithm we'll consider is log z, lowercase l, specific branch of the log, natural log of the modulus plus I times theta, and we're choosing theta between 0 and 2 pi. It's the same thing we did upstairs, except upstairs we took the theta value to be something different between negative pi and pi. And we had our reasons. It's because of the C1 and C2 stuff. Okay, and it's the same kind of computation. We'll integrate 1 over z, shouldn't have that logarithm there. We'll take the antiderivative, this branch of the logarithm, plug in the endpoints, and out pops another pi I. So, additivity of integrals. We know the integral over C1 plus C2 is the integral over C1 plus the integral over C2. We got pi I for both of those, so the integral is 2 pi I. We've integrated around a simple closed contour. We did get an integral of 0. We got an integral of 2 pi I. What's wrong with this 1 over z function? See, what did theorem 4.44 require? Required an antiderivative valid throughout D. Domain D and domain D contained the contour. That's the problem with 1 over z. Its antiderivative has to be a branch of the logarithm, and branches of the logarithms require cuts, branch cuts. And the branch cuts mess up the domain D, and then they violate the fact that the contour lies inside D, or they cut the contour if you like. So that's what's wrong with 1 over z. It's a logarithm thing. Its antiderivative is a logarithm, and that comes with branch cuts. I always like to say, well, I'm blaming the whole thing on polar coordinates, because somewhere in there is buried this multiple representation of points in polar coordinates. It's an argument problem that's caused it ultimately. Anyhow, that integral is not 0 around that closed contour. We computed it, so you see it ain't 0. And the reason that that theorem doesn't apply is we don't have an antiderivative on domain D, on which the function is defined and the antiderivative is defined. In this case, the 1 over z in the branch of the logarithm. But we can break it into pieces and add the pieces together. Let's take a look at the square root function. F of z equals z to the 1/2. Okay, that'll be defined in terms of a logarithm. So I got to tell you some stuff about the logarithm. We're taking the branch of the logarithm, it says, where the angle is chosen to be between 0 and 2 pi, excluding the endpoints. So this branch of the square root function is undefined for real numbers. So we've thrown out theta equals 0 or anything coterminal with it, and that would be positive real numbers. Of course, it's undefined at 0. And we'll take a contour from -3 to 3 that lies in the open upper half plane that only except for its endpoints. So the situation is shown in the figure down here. Here's contour C1. And they're going to have some other conversations in the book about C2. We're interested in C1. It starts at -3, and it does some stuff in the first quadrant, and it ends up at 3. Stays entirely inside, sorry, not the first quadrant, the upper half plane. Stays entirely inside the upper half plane. It doesn't go up and dip down. They've disallowed that. And we're going to be able, knowing nothing about this contour, except that it starts at -3, it ends at +3, and it lies in the upper half plane. And we're going to be able to figure out integrals. So there's must be some path independence with what's happening in terms of these integrals. If I can know nothing about the integral, nothing about the contour C1, except where it starts and ends, we must have some kind of independence for this type of function and those types of contours. Okay, so let's see, f of z, it ain't defined at z equals 3. Oh yeah, the branch of the logarithm requires that the branch of the square root function, we remove 0 and we remove the positive x-axis. So we've got this C1 containing 3. We've got two ways to deal with it. One of them is with a one-sided limit, I would prefer. The other is to appeal to the fact that I'm going to change the value of the function at a single point, the integrand, and that won't change the value of the integral. Single changes of the integrand don't change values of the integral. That's the way Brown and Churchill like doing it. So Brown and Churchill are going to replace the given branch of f of z, the z to the 1/2, with a branch f1, which is the same on all the points on the contour, except that it's defined at z equals 3. All right, this is effectively the same as taking limits. So the branch of the logarithm they're going to take is a different branch of the logarithm. It's got a branch cut along the negative imaginary axis. We're throwing out theta equals -pi/2. So what they're doing, similar to what we just saw, is they're saying define a new branch of the logarithm that removes 0 and cuts along the negative imaginary axis, and do it in such a way that we're creating a branch of the square root function. We get the same values throughout the upper half plane. We get the same values out of this new branch of the logarithm as we got out of the original branch of the logarithm, or this new branch of the square root function that we got out of the original branch of the square root function, except we're going to have it defined on the positive real axis as well. So all we're doing is changing the value of the integrand at one point, that point right there. That doesn't change values of integrals. All right. So we'll take the branch of the logarithm, the branch of the square root function z to the 1/2 to be e to the 1/2 log z, where log z is not the branch of the logarithm we had, but a branch that involves angles between -pi/2 and 3pi/2. We're interested in the upper half plane, so we're interested in angles between 0 and pi. This includes all all angles between 0 and pi. The original branch of the logarithm included all angles between 0 and pi, except for pi. So that's the problem that we're fixing. So anyhow, we've got agreement in terms of theta values between 0 and pi, excluding 0 and square bracket on the pi end. So between 0 and pi, we've got agreement, except at 0, but that's just a single point on the contour. and just a single point at which we're redefining the integrand in terms of points from the contour. So f1 of z and f of z, they're equal on the contour except at a single point, the contour. So the integrals will be the same. We could also do some limit stuff and we'd get the same thing out. I've kind of given in to Brown and Churchill's way of doing it. They do this repeatedly. Okay. The advantage of this new branch of the logarithm is we can find an antiderivative that's valid on a domain that contains c sub 1. And we're getting the exact same values out of the function, the branch of the square root, except at one point. Oh, well, if we can find an antiderivative that's valid along that contour, we can use theorem 4.44.a. An antiderivative of z to the 1/2, you wouldn't be surprised to learn, is 2/3 z to the 3/2, but I need to tell you what I mean by z to the 3/2 because that's a branch function as well. 2/3 modulus r to the 3/2 e to the I 3 theta over 2, and it boils down to telling you about the thetas. We're using a branch of the logarithm that's going to involve thetas between -pi-halves and 3 pi-halves. So certainly this is an antiderivative. The f1 lowercase f function is exactly the same as the original branch of the square root except at a single point. So if we want to evaluate the integral of the original branch of the logarithm, we're just going to replace that integrand with this function because they're exactly the same except at one point, the endpoint of c sub 1. So the integrals are the same, and we know how to evaluate this integral because we can find an antiderivative. It's this thing. So we'll use that antiderivative, this piece here in terms of polar coordinates, say. Then we'll have to write the endpoints in terms of polar coordinates. So we're integrating -3 to 3, so that'll be 3e to the I pi. Let's make that a little bit bigger. E to the 3i pi, that's -3. 3e to the I0, that's +3. So there's the endpoints we get out. Substitute in r equals 3 and these two different theta values. R equals 3 up here in the antiderivative. So we'll get 2/3, 3 to the 3/2, yeah, 3 in both of them. E to the I, 3 theta, upper value of theta 0, lower value is pi. So 0 here and a pi here. Do your arithmetic and out pops the number 2 square root of 3, 1 plus I. We didn't know anything about that contour other than it started at -3 and it ended at 3. Oh yeah, and it lied in the upper half plane. Now that being in the upper half plane, that was important because that let us use a branch of the logarithm. If all I know is it starts at -3 and ends at -3, if we had a contour that did a loop-de-loop around the origin, around 0 like that, we'd be doomed. Because if I had a loop-de-loop around 0, I can't do anything with that in terms of branches of the logarithm. I can't find a single branch of the logarithm that can fix it. I can break it into pieces like we did in that previous example, but otherwise we've got some issues with it. The point of this one is, gee, I didn't know much about that contour and we were able to evaluate the integral. I mean, we had to do it like this. I couldn't say, well, here's z of t or z of theta because I don't know anything about the contour other than it starts here, stops there, and it lies in the upper half plane. And with that little bit of information, we were still able to evaluate the integral. We'll see, not too far down the road, something called Cauchy's integral formula. We'll see when it is that you have this kind of independence of path and when you don't. And we'll spell that out in detail in section 50. So there's the use of antiderivatives to evaluate integrals. Check your hypotheses. That is, we need, the theorem says, we need an antiderivative. That antiderivative needs to be good throughout domain D on which the function is continuous, the integrand is continuous, And we need those contours to lie entirely inside this domain D. You got that going on, integrals are easy. As the punchline is. So we probably won't look at the easy ones, we'll look at the more interesting ones. And 1 over z, logarithms and square roots, branches things, that's where you get the interesting ones, because the branch cut usually disallows some of this kind of behavior. So that's the plan on antiderivatives as applied to complex integrals. And I think that's as close as we'll see to an actual fundamental theorem of calculus in here. There's some other generalizations you might see in a graduate course, but this is pretty much it for us. So have a nice day. I'll see you in section 46, I think it is. And we'll get into the some more stuff with the integrals and this exploration of when we don't get integrals of 0 and when we do. Have a nice day.